All right, question 2 says compute the following limits using series. And part A, we're looking at the limit as x approaches 0 of e to the x minus 1 over 5x. So the idea here is to trade in e to the x for its Maclaurin series. You see that here in green. And now note that these 1's in the numerator drop out, and that leaves us with x plus x squared over 2 factorial plus x cubed over 3 factorial and so on, all divided by 5x. Okay, now let's divide each term in the numerator by 5x. That's going to give us a fifth plus x over 5 times 2 factorial plus x squared over 5 times 3 factorial. And then we're going to get a cubic term, a quartic term, and so on. Okay, and since we're letting x approach 0, okay, all of these terms, aside from the leading term of 1/5, right, the constant term, all of these terms are going to go to 0. And so we conclude that the limit is equal to a fifth. All right, cool. So how about part B? Pretty similar. Okay, we have the limit as x approaches 0 of e to the 4x minus 1 minus 4x all over 16x squared. So again, we're going to trade in e to the 4x for its Maclaurin series. And here we're replacing x with 4x in the series for e to the x. Okay. Now note that the 1's will drop out and the 4x's will drop out up in the numerator. And so that leaves us with, well, 16x squared over 2, so that's 8x squared. And then here we have a 64x cubed over 6, so that's 32 thirds, and then that's multiplying x cubed. Okay, and then we're going to have a bunch of higher order terms, and then that's all divided by 16x squared. So if we divide each term in the numerator by 16x squared, that's going to give us a half plus 2/3 x plus higher order terms, right? So up here, right, we would have a quartic term and then a quintic term, so on and so forth. And when you divide all of those higher order terms by 16x squared, okay, it's going to start out as something quadratic, then cubic, and so on. And since we're letting x approach 0, just like we saw in part A, all of these terms, aside from this lead term of a half, are going to go to 0. And so the limit is a half. All right, cool. So now let's go ahead and make some space. Check out part C. All right, so for C, looking at the limit as x approaches 0 of 3 times the tan of x minus 3x minus x cubed all over 7x to the fifth. Okay, now we don't have a series representation for tan x in the 10.4 worksheet. Okay, but notice right below the limit, I give you the first 3 non-zero terms of the Maclaurin series for the tangent of x, and just so happens that this series converges to tan x on this interval where x is strictly less than pi over 2 in absolute value. Okay, but in any event, let's go ahead and trade in tan of x for this series. And now let's go ahead and distribute this 3. So that's going to give us 3x plus x cubed plus 2/5 x to the fifth, so on and so forth. And then we still have our negative 3x and our negative x cubed. That's all divided by 7x to the fifth. Okay, now the 3x's are going to drop out and the x cubes are going to drop out up in the numerator. Okay, so that leaves us with 2/5 x to the fifth plus higher order terms. And that's all divided by 7x to the fifth. So dividing here gives us 2/35 plus higher order terms, right? So up here, okay, we would next have a degree 6 term and then a degree 7 term and so on. And so then when you divide by 7x to the fifth, that's going to give you a linear term, then a quadratic term, and so on. And see, as you let x approach 0, all of those terms are going to go to 0, leaving you with just this 2/35. All right, cool. And then for the very last one, D, we're looking at the limit as theta approaches 0 of sine theta over theta. So we can go ahead and trade in sine theta for its Maclaurin series. That's theta minus theta cubed over 3 factorial plus theta to the fifth over 5 factorial, so on and so forth. And then we're dividing by theta. So let's go ahead and divide each term in the numerator by theta. And so we get 1 minus theta squared over 3 factorial plus theta to the 4th over 5 factorial, so on and so forth. And now as we let theta approach 0, as we've seen now with all these others, right, all of these terms aside from this leading term of 1 are going to go to 0. And so here we get that the limit is equal to 1. And you might have seen this limit back in Calc 1. It's typically derived there using the squeeze theorem, because it's an important result in showing that the derivative of sine theta is equal to cosine theta. But in any event, that's going to do it for this question. I will see you in the next video. Thanks.